Hello, I'll be doing a heating pro processes test prep the physics test tomorrow. Prep physics next time? Doesn't matter. I'm putting the title of the video. Yeah? Okay. So basically you have a question. Here's a question. It says a blacksmith is testing the thermal properties of a 0.4 kilogram block of copper. The copper block is heated in a furnace to exactly 250 degrees Celsius. It is then quickly transferred into a perfectly insulated calorimeter, calorimeter, okay, yeah, containing a mixture of 0.25 kilograms of liquid water and 0.05 kilograms of solid ice. The water and ice mixture is currently sitting at a thermal equilibrium at exactly 0 degrees Celsius. And it asks us what is, assuming no heat is lost to the calorimeter and it's on the environment, to the calorimeter or the environment, calculate the final equilibrium temperature of T final of this entire system. So first let's write all the things we need to know, right? So first we do the copper, right? Oh my gosh, copper. And we have the mass Cu copper is 0.4 kilograms, and the C of Cu, which is the heat capacity, is 390, and the initial temp Cu is 250. I'm gonna write water, right? So water in the calorimeter. So we're not even gonna write that. Okay, yeah, we're gonna do it. So it's the mass of water is 0.25. C of water is 4180. Temperature of water is 0. Ice. Mass is 0.05 kilograms. C. I is. I actually don't need to know this because the ice is increasing in temperature. So we don't need to know the latent heat of ice. We're going to write L. That is 3.34. The formula sheet. Times 10 to the power 5. The temperature of ice is 0. First, we're going to write Q gain equals Q lost. So I'm going to write the Q gain, which is water first. So 0.25 times 0. Actually, that's not right. We'll write mass of water MC delta T plus MIL plus MI C water delta T equals Q loss is MCU CCU delta T. That's basically the equation. So we're going to sub numbers in now. So we're going to say 0.225 4180. T delta T is T final take 0 plus it'll be ice is at 0.05, 3.34 times 10 to the power 5 plus mass of ice is 0.05 4180 times TF take 0, and that equals 2.4 times 390 times 250 take TF. Now we can simplify this. So these two have a common multiple, which is TF. So we can just calculate those two together. And TF takes 0 as TF anyway. So we're just going to do 0.25 4180 plus 0.05 times 4180, which gives us 1254 TF, plus the middle one, which is 0.05 times 3.34 times 10 to the power 5, just 16700. And this equals 0.4 times 390. We're gonna get that, sir. So take 156 TF. So we did that first, because now we can just times 250 to get the number in front, which is easier on for the calculator. Now just rearrange, and 397. It's good on either side, but I like keeping it positive. So I'm gonna use 39000 to take 16700. We get 22300, and we put that to that side, it will become positive. So it's 1254 plus 156, 1410 TF, and TF will equal to this divided to this side, which is 22300 divided by 1410, which gives 115.8156 degrees Celsius, which equals to 15.8 degrees Celsius, because in physics we always round to 3 decimal points. And for part B of this question, it says, after the experiment is over, the blacksmith pours the leftover warm water in a wide open metal pan. To cool the water down quickly, they set up a high-speed fan to blow the dry air directly across the surface of the water. Use the kinetic theory of matter explained. Okay. So basically, we have 4 things we need to write. So firstly, we need to say how the water is cooling, and because with a fan increase the cooling, we need to know why it's cooling first, right? So wait, the question says, yeah, to cool the water down quickly. Why the water is cooling? And part B, right? Why is the water is cooling? So basically, in liquid water, different sections have varying kinetic energy, and then due to convection, due to convection, the hot water, I think we're right. Wait, let's make sure we're right. Let's make sure. Yes, I think I'm right. Actually, we're trying to find if the warmer stuff actually goes up or down to prove our point, because we can prove it some other way. Warm molecules move up, so we're right. Hot water will go up, and because they move up, because the so hot water go up, and particles with high enough kinetic energy at the surface will break their intermolecular bonds and to molecular bonds and evaporate. And it's basically how they get cooler. And so basically now we're going to talk about the fan. This brings the hot, oh wait, no, we're just right. The fan takes the hot vapor away from the liquid, stopping it from stopping them from condensing back and allowing more molecules to evaporate by taking away the vapor for space for more. And now I have to relate it back to the question, and I'm gonna say because the particles with the highest kinetic energy left as vapor, the average kinetic energy average kinetic energy of the remaining liquid will decrease with the fan speeding up the process. Yep, and that's one of the relevant questions and pretty useful questions for me for my revision of this test. All right, bye bye.